Okay, so what I want to do now is generalize the Lagrange multipliers theorem even more to the case where we have more than one constraint. I wrote the word several, but we're going to state it for two. Two is several, after all. So here's the theorem. I'm not going to prove it or discuss the geometry. Our discussion in the two-variable, one-constraint case was sufficient. So let x0, y0, z0 be an extremal point of the function f of x, y, z, which is a C1 function, subject to two constraints, g of x, y, z equals 0, and h of x, y, z equals 0, where in the single constraint case, we had some assumptions here. So first of all, we're assuming h and g are C1 functions also. And then we had an assumption about the gradient of the constraint not vanishing. Remember that? That has to be replaced by something here. It would be naive to say, okay, let's assume that the gradient of g and the gradient of h don't vanish. But it turns out to be something slightly more, I don't want to say difficult. And the gradient of g and the gradient of h are linearly, I'm going to throw an algebra word, or algebra, two words at you, linearly independent. This is an E, right? Independent. At x0, y0. So what does it mean for these two vectors to be linearly independent? Wait. What is it?
x0, y0, z0.
Z0, of course. Thanks. Z0. What does it mean for two vectors to be linearly independent? And that's how you generalize it to more than two constraints. This statement generalizes. In the case of two, being linearly independent means that one is not a scalar multiple of the other. Do you agree? And in particular, it means that none of them could be 0, right? Because if one is 0, it's 0 times the other. So it says more than just saying that neither one is 0. It's saying that this is not 0, this is not 0, and one is not a multiple of the other. Okay? When there's only one of them, all that remains is the statement that that one is not 0. A single vector is a linearly independent set if it's not the 0 vector. Okay? You learned this term in algebra, right? You know what I'm talking about. Okay. And what's missing from the theorem? Is this the entire theorem? Right. Then there exists. Okay, good. Then there exist, and there are going to be two Lagrange multipliers now. I'm going to call one lambda, and the other one I'm going to call mu. Mu is the Greek m, which follows the Greek L, which is lambda for Lagrange. So there exist L and m, lambda and mu, such that, and the way we're going to write it is the following: the gradient of f plus lambda g plus mu h at the point x0, y0, z0 is 0, the 0 vector. So that's the theorem. Okay, so does everybody agree that this generalizes the theorem that we had when there was only one constraint? Okay, clear? Okay, let's do an example. Let's just do an example. So example, we need a target function, f, and we need two constraint functions, g and h. So f of x, y, z is going to be the function x plus y plus z. That's the target function. g of x, y, z, this is the first constraint, is going to be x squared plus y squared minus 2 equals 0. And h of x, y, z, that's the second constraint, is going to be x plus z minus 1 equals 0. These are the two constraints. And I want to find maxima and minima. So the first thing I have to do before, I'm going to use the Lagrange multipliers theorem. The first thing I have to do is check that all the conditions hold. First of all the smoothness conditions, the fact that these three functions are C1 is rather obvious. Do you agree? Okay, so f, g, and h are all C1 on the entire R3 space, so that's a non-issue here. Does everybody agree? Now I have to check the gradient business, that the gradients are linearly independent. So what's the gradient of g? The gradient of g is a vector of the three partial derivatives. So it's 2x, that's the derivative of g with respect to x, 2y, that's the derivative of g with respect to y, and 0. That's the derivative of g with respect to z. Does everybody agree? What's the gradient of h? 1, 0, 1. Does everybody agree? So what do we have to check? We have to check if these two are linearly independent. Is the gradient of g, can it ever be a multiple of the gradient of h? A non-zero multiple, right? Two vectors are linearly independent if one is a non-zero multiple of the other, okay? Or a zero. It can never be. Do you agree? Well, not exactly. When might it be?
X equals a half and
Not a half. That won't work. But when x and y are both 0, then the gradient of g is 0 times the gradient of h. In fact, the gradient of g vanishes then. Okay? So these are linearly independent, unless we're looking at points of the form x equals y equals 0. Do you agree? These points are problematic, but these points don't satisfy the constraints. Therefore, we don't care about these points. Why? Because if x and y are 0, then minus 2 is not equal to 0. These are not points which satisfy g, and in fact, they don't, well, they could satisfy, depending on z, they could satisfy h, but they don't satisfy g. Do you agree? Okay? But a point of the form 0, 0, something does not satisfy g equals 0. It doesn't satisfy the constraint. It's not a point we're looking at. Clear? So we check the conditions of the theorem. The functions are C1. The gradients are linearly independent on points which satisfy the constraints. Clear? Everybody? Now we have to use the then part of the theorem, the exist, lambda, and mu, etc. We're going to get a system of how many equations in how many variables. Think for a minute. Let's look back here for a second. How many equations, how many variables? Five is correct. There are going to be 3 equations originating from this, from the gradient vanishing. The equation, the derivative with respect to x of f plus lambda g plus mu h equals 0. The derivative with respect to y equals 0. And the derivative with respect to x, to z equals 0. Those are 3 equations. And 2 more are g equals 0 and h equals 0, satisfying the constraints. Total of 5 equations. How many variables? 5. Lambda and mu, and x, y, and z. Okay, let's write all that. So in general, let me write them in general first, and then we'll extract what they are for this specific example. So the equations that we have are fx plus lambda gx plus mu hx equals 0. That's one equation. Fy plus lambda gy plus mu hy equals 0. Fz plus lambda gz plus mu hz equals 0. These are the three equations already originating from the gradient. And in addition, g equals 0 and h equals 0. Do you agree? Let's write what they are for our specific example. So what is the derivative of f with respect to x? F is just x plus y plus z. The derivative is 1 plus lambda. What's the derivative of g with respect to x? 2x. Okay, so keep an eye on what g and h are. Tell me if you agree. So it's 2 lambda x plus mu, the derivative of h with respect to x, which is 1, plus mu, and this equals 0. This is the first equation. Good? Everybody with me? Okay. The second equation, the derivative of f with respect to y is 1, plus lambda times the derivative of g, so it's 2 lambda y, plus mu times the derivative of h, but the derivative of h is 0. So this is all that remains from the second equation. Third equation, f with respect to z is 1, g with respect to z is 0, mu times h with respect to z is 1. So plus mu equals 0. And I have to write g and h. X squared plus y squared equals 2, and x plus z equals 1. This is the system of 5 equations in 5 variables, x, y, z, lambda, and mu. Good? Everybody? Questions? Okay, now I have to solve it. And again, it's not a linear system. There are some nonlinear terms here. And you can solve it whatever way you want. For example, it's easy to see from here that mu is negative 1. Okay? Remember, I don't care what mu and lambda are, but they're auxiliary. I can use them. So from here, for example, I can see that mu is negative 1. Okay, so let's see how I solve this. Mu is negative 1. I plugged it into here. So from this, I get, from this equation, that mu is negative 1. It cancels with this one. So I get 2 lambda x equals 0. Do you agree? So 2 lambda x equals 0 could happen in 2 cases. Either lambda is 0 or x is 0. One of them has to vanish in order for this to be satisfied. If lambda is 0, equation 2 gives a contradiction. Do you agree? So lambda cannot be 0. So from here it follows that x has to be 0. So I'll continue here. Lambda is not 0. Contradicts equation 2. Therefore, x is 0. So here's the second variable revealed. Good? Okay, what did I do now? I plugged it in here into equation number 5. So if x is 0, what is z? Z has to be 1. Okay. By the way, when you write a solution in your notebook on an exam or whatever, anything you're going to hand in, don't write like this with arrows all over the place. It's very confusing because you're not standing there to explain what you're writing to whoever's reading it. Okay? So write it completely linearly. Write everything we're seeing, right? From the third equation, we see that mu equals -1. We plug it into the first equation, we get that 2 lambda x equals 0. Lambda is not 0 because it contradicts the second equation, therefore x equals 0. We plug it into the fifth equation, do that. Okay? Never write a bunch of arrows all over the place. Okay? Okay. So I'm not giving you a good example right now, but I'm saying it. I'm here to say it, so it's legitimate. So z equals 1. I'm going to then plug what? Into equation 4, x equals 0. So what do I get from here? X is 0, so y squared equals 2. So y has two possibilities, plus or minus root 2. Right? And finally, I'm going to use equation 2, now that I know y, and I can find lambda, but I'm not going to do that, because I don't care what lambda is. Right? I only care about x, y, and z, and I found them. I did find mu along the way, but it's auxiliary. I can do that, but I don't need now to go back and find lambda. I'm saying the stuff I'm babbling about is longer than just doing it, but there's a point here. I don't need to find lambda and mu. Clear? Okay. So we found 2 points. Let's write it here. Critical points. Critical points that we found are x was 0, y was either root 2 or negative root 2, so we have 2 of them, and z is 1. So these are the 2 points that we found. We can calculate the value of the function at these 2 points. Okay, so let's call this point P1, and let's call this point P2. The value of f at the point P1 is what? I'm just plugging these into f. F was x plus y plus z. So the value of f at P1 is root 2 plus 1. The value of f at P2, x plus y plus z, is minus root 2 plus 1. Do you agree? So is it fair to say that this is the minimum of f and this is the maximum of f? It will be fair to say, providing I can justify first that f indeed has a minima and a maximum. Okay? Because then these are the only critical points. So for that I have to look back at our example and see, can I say that? Okay, so let's look back at our example. So f is a continuous function. I want to use Weierstrass. That's the only tool that I know. Okay? I want to argue using Weierstrass. F is a continuous function. Is the domain closed and bounded? So what's the domain? The domain are all the points x, y, z in R3 that satisfy both this and this. Do you agree? What is h? Geometrically, what is h? Five-letter word starting with P. Point. Plane. H is a plane. It's ax plus by plus cz plus d equals 0. Arrgh. Does everybody agree that this is an equation of a plane? H is a plane. Do you agree? Is a plane closed and bounded? No, it's definitely not bounded, right? A plane is infinite. Do you agree? But that's not what I'm looking at. I want all the points that satisfy both H and G. What is G? This is not a...
It's a shape.
It's a shape. Good, good. Come on, you guys.
It's a circle. A ball.
It's not a circle. It's not a ball. It's a cylinder. It's all the points x, y, z that satisfy x squared plus y squared equals 2. So for every z, you get a circle of radius root 2. It's a cylinder. Okay? Who taught you quadratic surfaces? Who was your teacher? Did a bad job. Come on, you guys have to go over this stuff and to know it. This we're going to use it all along. We're starting integrals soon, very soon, and it's going to be all over the place. Please review that stuff. Okay? Seriously. I'm serious. See? Serious. Review it. Okay. So this thing, G and H, G is a cylinder, H is a plane. What's the intersection? Right, it's some form of curve, which could be either a circle or a twisted circle, an elliptic-like thing. It's closed and bounded. Do you agree?
But wouldn't that be unless the ellipse in the plane?
Right. You have to verify, and this is not the case. If the plane, if the cylinder is a cylinder with the z-axis as its symmetry axis, do you agree?
Yeah.
The cylinder has the z-axis. If the plane were like this, the intersection might have been different, right? But this plane is not a plane which is parallel to the z-axis, right? Z varies, x varies, so it's tilted. Do you agree?
What?
The normal to this plane does not only have x and y components, which would have to hold in order for it to be like this. The normal has a z component as well. Okay, so this surface, the intersection of these two constraints, points satisfying both constraints, lie on some curve, which is the intersection of a plane and a cylinder, and that curve is closed and bounded. Therefore, the domain is closed and bounded by Weierstrass, continuous function, closed and bounded domain, has a minimum and a maximum. Okay, so let's write all that. The intersection of G equals 0, which is a cylinder, and H equals 0, which is a plane, is closed and bounded, is a closed and bounded curve. F is continuous. Hence, by Weierstrass, F has a minimum and a maximum subject to these two constraints. Subject to these constraints. And by checking these values, these were the only critical points that we found. And this curve, it's the intersection of a plane and a cylinder. So it's a smooth curve, no corners to check at, right? So these are indeed the only critical points. So we can deduce that P1 is a maximum and P2 is the minimum. Clear? What I want to do is give you a homework problem, okay? And the homework problem, I'm not going to solve it on the board. The idea of the solution is very, very similar, but the conclusion is different. And the conclusion is different because you have to pay attention carefully when you solve it and observe that the domain, the intersection of the constraints is not closed and bounded. And the points that you're going to get end up being two local minima, both of them. Okay? And you can figure that out if you figure out what the shape, as you said, of the constraints is. Okay? So example, find points which are closest and farthest. Do you say farthest or furthest? Like this? Is this right? You? From the origin. So we did something similar. Finding a point that's far or close to the origin, we do it by taking the function f of x equals x squared plus y squared plus z squared and maximizing or minimizing it, just like we did for that ellipsoid. Remember we did that? Okay. So that's the function you're going to use. On the curve obtained by intersecting the cone z squared equals x squared plus y squared, and you should recognize right away that this is the simplest circular cone centered at the origin with the z-axis, its symmetry axis, and the plane x plus y minus z equals negative 2. Now, when a plane intersects a cone, those are what we call the conic sections. Remember them? Remember we discussed the conic sections? If it intersects it at a certain angle, what you get is an ellipse or a circle or an ellipse, which are closed and bounded, and everything's fine, just like in the previous example. But if it intersects it in a bigger angle, which is bigger than the line which generates the cone, then what you're going to get is a parabola or a hyperbola, which are not closed and bounded, right? A hyperbola is not a closed and bounded curve, and the Weierstrass theorem is not going to hold, okay? And in this case, the intersection is in hyperbola, and you have to figure that out. And since it's at a hyperbola, the points you're going to get, the two candidates you're going to get, if you do the Lagrange multiplier business here, okay, the points you're going to get are the two minimas, the closest point to the origin on the upper branch and on the lower branch. And there is no maximum. There is no point on a hyperbola that's farthest away from the origin. Is that clear? Is the geometry clear? But it's not obvious when you just look at it. You have to figure it out. Okay? So, homework. Okay, do it. It's a very important exercise. It exhibits the idea why I've been so strict on checking and verifying this Weierstrass business before I classify minima and maxima. I just want to add one more quick remark. Remember for local minima and maxima, we had the second derivative test, which allowed us to classify if, what was it, AC minus B squared is positive or negative or equals 0, then it's a minima or a maxima or remember that theorem? There's a constrained version of that. Okay, there's a constrained second derivative test that allows you to classify using second derivatives for constrained extrema. I just want you to know it exists. It's usually not in the material of this course, but I want you nevertheless to know that it exists. And if you need it, you can look it up. Okay, so the constraint second derivative test for classifying local minima and maxima or global under constraints, under this Lagrange multiplier or whatever way you use business. Okay, so that's the end of this.